What's up, guys? This is Jahangir from Emporium, and today we're going to be talking about acids and bases in salt solutions. So, this is a little bit different than just acids and bases in a regular solution. So, one of the first things we need to talk about is salt hydrolysis, or there's also solvolysis, I believe that's another term, but we'll just refer to it as salt hydrolysis. So, salt hydrolysis. So if we remember from maybe past biology vocab, we know lysis is the breakdown, hydrogen is water. So salt hydrolysis is sort of when ions have dissociated from the salt to form either hydroxide or hydrogen ions. So it's kind of like dissociating the salt. So if we write that over here, we could put when ions dissociate from salt to form hydroxide or hydrogen ions, and also or hydronium. And let me actually change this. This indirectly affects pH. The reason why is that if we have more of a dissociation of salt to form hydroxide or hydronium, then this affects pH, because if we have more concentration of hydronium, we have a lower pH. If we have more concentration of hydroxide, we have a higher pH. So it's sort of this indirect relationship in which salt hydrolysis can actually indirectly affect pH. So let's talk about basic salt solutions. So a basic salt solution, this will only form if we have a weak acid and the conjugate base is an anion, which most of the time the conjugate base will be the anion. But the main thing to point out with in a basic salt solution, this is when we have a weak acid, and we have an anion, and I'll just put plus anion of conjugate base. So what does this even mean, you might be wondering? Well, if we remember from our understanding of weak acids and strong acids, weak acids don't dissociate completely. And one of the biggest conceptual things you need to understand is that if we have a weak acid, then we have a stronger base. Now, it's not going to be a legit strong base like our ones from group 1 and group 2, because those are our real strong bases. But it's sort of as if we have a weak acid, then we compensate for having a stronger base. And it's kind of this seesaw effect, where if we have a weak base, then we're going to have a stronger acid. So it's kind of relating the strength of both, where if the strength of an acid is weak, then the strength of the base will be stronger. If the strength of the base is weak, then the strength of the acid will be stronger. So it's a sort of seesaw kind of balancing effect. I guess you could sort of think of it that way. And what we're going to have is something like this. So this A minus is our conjugate base, which is our anion. And in equilibrium, this is going to form our weak acid plus OH minus. And this is exactly what we're going to see. We see this conjugate base, which is the anion, and the strength of this conjugate base is stronger than this weak acid. So what's going to happen is this hydrogen over here from the water will go to the conjugate base to form our weak acid, and over here this will be our OH. So this is sort of what occurs in a basic salt solution, because our acid over here is weak. When we have a weak acid, it doesn't dissociate completely, so we're going to have a stronger base. So that's pretty much what a basic salt solution looks like. Usually you're going to have a weak acid, And if you have weak acid, then you're going to have a stronger conjugate base. The conjugate base is going to be an anion, and that's what sort of forms this basic salt solution with this OH minus, this hydroxide. So let's go through a practice problem real quick to sort of illustrate this concept. So the question asks us to find the pH of a 0.10 molar solution of NaOCl. And yeah, that's pretty much what the question is asking. So to break down this question, we're given one of the anions. And usually when we're looking at these sort of molecules, we have to break them apart. So we have sodium and we have OCl. So sodium is a group 1 element, and we could just pretty much forget about this, because if we do NaOH, this forms a strong base. So the reason why we sort of kind of forget Na is because this is just going to form a strong base. And when we form a strong base, our acid is pretty much going to be neutral. So anytime you see these group 1 elements, or anytime you see anything that could potentially make a strong base, like NaOH or LiOH, anything like that, you see those group 1 or group 2 elements, you pretty much forget about them. Because when those strong bases react, they form a very, very weak acid that pretty much is neutral. And we're not trying to look at that to find our pH, because that's just going to produce a neutral pH. So we're looking primarily at this OCl minus. So what happens is, if we write this equation, H2O and those double bars of HOCl plus OH minus. So this is a weak acid. Reason why it's a weak acid is because it's not part of our So I Brought No Clothes acronym. And since this is a weak acid, we're going to have a stronger conjugate base. Our OCl is a little bit stronger. So we have a Rice table again. And what happens is we're given our solution, or our molars of 0.1. So we have 0.1 is our initial. Our water, which we can just forget since it's just a liquid form. And over here, our HOCl, that's going to be 0. Our hydroxide is going to be 0 because we're not given those concentrations. So what happens now is we just do our usual Rice table, XX. So this is going to be 0.1 minus X. And we have those X's over there, or I forgot to put pluses over here. So that's pretty much what we have so far. Now, this is going to equal our Kb because we're dealing with hydroxide, so this is going to be x squared over 0.1 minus x, but we don't know our Kb. Now, to find our Kb, we need to use this formula over here. Kb equals Kw over Ka. This is our base ionization constant, acid ionization constant. I believe this is the auto ionization of water. So what's going to happen is we know our Ka, and like I said, the exam should give you your Ka, but if they don't, they should give you some sort of like formula sheet showing each element or just chemical equation and what that Ka is. But our Ka for this reaction is going to be 4.0 times 10 to the negative 8. And this is the Ka specifically for our weak acid, because remember, Ka is the acid ionization constant. The only acid we have is HOCl, which is a weak acid. And remember, these Kas mostly apply to weak acids. So if we have our Ka right there, then all we have to do is 1.0 times 10 to the negative 14, which is the auto ionization of water, over 0.4, or my bad, 4 times 10 to the negative 8. And what we get is 2.5 times 10 to the negative 7. And now since we have this number right here, then we could just make this equal. So this is going to equal 2.5 times 10 to the negative 7. First, you want to find your percent ionization. So first, assume that this X is negligible at first. Then you multiply 0.1 times this and square root that. So times 0.1, square root that, and you divide that by 0.1 times 100, and you're going to get 0.16%. That's less than 5%. So now we can keep on going. And if you do all the math, our x is going to be 1.6 times 10 to the negative 4 molars. And this is our hydroxide concentration. So we need to find our pOH, which equals this negative log of 1.6 times 10 to the negative 4. And our pOH is going to equal 3.8. We know that pH equals 14 minus pOH, which is going to be 14 minus 3.8, and that equals 10.2. So that is our answer for finding the pH of 0.1 molar solution of NaOCl. So what are the things you want to realize? And we'll actually talk about why you need to eliminate this, but you need to eliminate those group 1 and group 2 ions that you see over here. And when you're trying to find the pH, more than likely this over here, that OCl, if you add an H to it, then it's going to be a weak acid. When you see something like OCl, if you see something that's not so I brought my clothes, if you don't see something like at the end, you don't see Br, you don't see Cl, you don't see all of those ions that don't have hydrogen. Like remember, if we had these H's over here, they become strong acids. So if you don't see this little ion over here, Br, if you don't see Cl, if you don't see SO4, if you don't see any of those, then that means it's not a strong acid. So one of the key things that I like to do is try to add an OH over here and try to add a H over here. And ask yourself, does this become a strong base? Or does this become a strong acid? And this becomes a strong base. So if it becomes a strong base or strong acid, you pretty much forget it. And if it becomes a weak base or weak acid, then you have to pretty much use it for your for pretty much solving any of your questions. So now that we know that, let's move on to acidic salt solutions. So this is a little bit different from our basic salt solutions. So we'll write acidic salt solutions. So in acidic salt solutions, this is going to be, we're going to have a cation. So a cation is a positively charged ion, and this is going to be the conjugate base of a weak acid. So just to pretty much summarize here, you're going to have a weak base, and let me do this. The conjugate acid will be, and we'll put cation. So in this scenario, when we have an acidic salt solution, we're going to have a weak base. When we have a weak base, our conjugate acid will be a little bit higher in strength. So what we're going to have is a conjugate acid, and we add plus H2O, double bars over here, and we have our base, which is going to be weak, plus hydronium ion. Now you might be wondering, well, this looks different from our usual equation, which is those double bars, and then we have our conjugate acid plus OH minus. The reason why is because in salts, we have cations and anions. We have positively and negatively charged ions. In this equation over here, the base is just reacting with water. But in the acid salt solutions and also the base salt solutions, in this acid salt solution specifically, this cation over here will react with water to produce hydronium. In the base, if we go back up here, this anion over here, which is our conjugate base, will react with water, and that will pull a hydrogen to become a weak acid, to become our HA. So These anions and cations are the biggest sort of difference between a basic and acidic salt solution versus just a normal solution. Because in a normal solution, such as water, if we add a base to water, the base is only reacting with water. But if we add a salt solution, now the cations and anions start reacting with the water. And this is why we see when we have a weak acid, the anion of the conjugate base, that anion is going to start reacting. So these anions and cations will start getting into the action. And it's not just going to be the bases and the acids reacting. It's now going to be anions and cations reacting. So that's the number one thing you need to know about these salt solutions. It is that the cations and anions are reacting, and this sort of flips the script. It switches up everything. Like over here, usually we're going to have HA, our weak acid, plus H2O, and that goes to A minus plus hydronium. So right here, it is the weak acid over here that's reacting with the water to produce hydronium. Over here, it is the anion that is reacting with water to produce hydroxide. So it's a sort of flip the script type of motion, where when you have this anion, it's negatively charged, it's going to take that hydrogen and produce hydroxide. And over here, in that acid salt solution, what's going to happen is this cation will give away one of its hydrogens to become this sort of weak base that we're talking about. So I'm going to emphasize this one more time. The salt solutions, the anions and cations are reacting. Those are the main ones that are going to be reacting to form these sort of hydronium ions or hydroxide ions. So if we have a cation, we're going to be forming these hydroniums. If we have an anion, we're going to be forming these hydroxides. But this is assuming that we have a weak acid and a weak base. Because if we have a strong acid, strong base, then it really doesn't matter, because those acids and their strength will take over to produce a higher or lower pH. And remember, if we have a strong base, then we're going to have a higher pH. If we have a stronger acid, we're going to have a lower pH. So just remember, look at the cations and anions for these salt solutions, because those are what take over when we have weak bases and weak acids. So now that we know that, and actually let me just label this just as reference. So this is our conjugate acid. Conjugate acid is going to be reacting, or our conjugate acid, which is our anion or cation, my bad. So cation is going to react with this water to produce our weak base, weak base, and this hydronium over here. So now let's talk more about these metal ions and how they affect pH. So like we talked about, these metal ions indirectly affect pH by increasing the concentration of hydronium and hydroxide. So one of the key points you need to know, and I'll just put a dash right there, is that the smallest, let me actually change my font over here. The smallest and highly charged metal ions, and these include things like Al3+, Cr3+, iron 3, we have Bi3+, and there's more. But these small, highly charged metal ions indirectly, so I'll put indirectly, they indirectly decrease pH. So you might be wondering, well, how do these small, highly charged metal ions even decrease pH? How do they even do that? Well, if we remember from our past discussion of strengths of acids, we remember that if we have something electronegative, it's going to pull the electron density to itself, make the OH more polar, and it allows the hydrogen to be much basically allows that hydrogen to ionize much easier because that OH becomes more polar because our electronegative atom is basically pulling electron density. It is electronegative, so that's what it's pretty much doing. And Al3+, Cl3+, all of these have a high Coulomb force. And if you remember Coulomb's law, it's talking about distance and also charge. So if we have smaller distance, a small radius, and we also have a higher charge, then these metal ions are going to be pulling the electron density towards itself. So to kind of illustrate this, I'm going to draw a diagram of what this might look like. So I'm going to draw out a molecule AlH2O63 plus, and I'm going to scroll down a little over here. So let's move that there. And I'm just going to draw my loose structure, or it's not a loose structure, but just sort of a diagram showing what this will look like. So let's do, and I'm having a hard time picking which color I want to use. All right, so actually, yeah, I think that's good. That's decent size. So these are going to represent our oxygens, and let's just down this a little to our hydrogens. So this is H2O, 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 another H2O, and our final H2O. So let me change this over here. This is going to be our aluminum 3+ bonded to all these waters, and I'm just going to write this down as water over here. And these are our waters, and the reaction is going to be in water. So let me actually just copy this, and let's cut this out. And here's something I'll do to replicate what's going to happen. So this is our water over here. This is our AlH2O63+. So what this is going to turn into, and let me actually copy paste this. This is going to turn into, no, let me cut this out. This is going to turn into forgot the L, AlOH, H2O, 5, 2+, and then plus our hydronium. So here's what I mean when I'm talking about these small, highly charged metal ions and how they can indirectly decrease pH. So Al3, like we said, is a small, highly charged metal ion. And this Coulomb force is actually pretty high because we have a small distance and a higher charge. So this guy over here is going to pull the electron density. It's pretty much grabbing all the attention from all of these molecules over here. And this OH bond from that hydrogen, it's going to become more polar. And like we talked about from our previous videos, if a bond becomes more polar, it's much easier to ionize. So this water over here will take that hydrogen over here and turn into hydronium. And this is how this Al, and actually let me put a minus charge, or that Al, the aluminum, is going to take all the attention, take most of the electron density, and when that happens, it's easier for this hydrogen to just move away because this Al, all these oxygens are attracted to the Al, and they have just this sort of third wheel over here. They don't really need that hydrogen because this aluminum is attracting all the electron density. It's hogging all the electrons, all the attention, and this water over here just pretty much takes on the hydrogen because it's easy to ionize and it's easy to take. So this is kind of similar to how we talked about of those highly electronegative atoms and how they take most of the electron density because they have the OH bond, they make that more polar, and that can ionize easier. So that's another one of the concepts you have to understand is that small, highly charged metal ions or just elements that are electronegative will pull the electron density, will make the OH bonds more polar, and they allow hydrogen to be ionized much easily, which decreases pH because we're increasing the amount of hydronium ions we have. Now that we know that, let's go through this practice problem. So it says predict Predict if these salts are acidic, so acidic, basic, or neutral. All right, and some of the salts that we have, and let me just change the color over here. So we have, one of them is Li, lithium iodide, I believe that's how you pronounce it. Then we have, over here we have NH4NO3. Then we have, C, we have SrNO3 2. D, we have KNO2, and C, we have, or E, we have NaCN. So the first step in solving any of these questions is breaking up your ions and seeing if it's a strong base or a strong acid. So let's go to A automatically. And with the first one usually if you add an OH, then you can see if it's a strong base. And over here on the second one, if you add an H, then you could see if it's a strong acid. So Li, if we do LiOH, oh, that's a strong base, so we have to eliminate that over there. And if we do Hi, well, that's strong acid. Strong base, strong acid, when they react in a salt solution, they're going to produce a neutral pH. So for this one over here, we can say it is neutral, because we have a strong base, a strong acid. When they both react, they produce a neutral pH. So we got A out of the way. Now let's look at B. So B, when you add NH4 and you add OH there, doesn't really produce a strong base. So we're good on that part. But over here, HNO3, that's one of our strong acids. So we write this one off. Now, if we write NH4, this is going to be NH4 plus. And remember, cations are usually going to be the ones that are acidic. So we write acidic over here. Because if we scroll back up to our acidic salt solutions sort of definition over here, our conjugate acid is going to be a cation. So if your conjugate acid, or pretty much if you have a cation, then you can assume that it's going to be in an acidic solution, because our cation will react with water to form hydronium. So when we have cations, you can assume that it's going to be an acidic solution. And when we have anions, you can assume that it'll be a basic solution, because when anions react with water, they produce hydroxide. When cations react with water, they produce hydronium. They produce a lower pH, an acidic pH. So NH4 over here, that is going to be acidic. So when you've eliminated your strong acids or strong bases and you have a weak acid or a weak base, try writing out or seeing if it's a cation or an anion. If it's cation, more than likely it's going to be an acidic solution. If it's an anion, more than likely it's going to be a basic solution. And if you know that, then everything pretty much becomes easier. So over here, SrNO3 2. So Sr over here is going to be a 2 plus, so that's a group 2 element, so we can automatically eliminate that, because group 1 and group 2 elements, they're usually going to be the ones that are strong bases. And if we write SrOH2, I believe that is one of our strong bases, because it's group 1 or group 2. And NO3 over here turns into HNO3, and that is a strong acid. And now this is neutral. So I actually forgot to put acidic over here. Acidic. This is going to be neutral, because we have a strong acid and strong base. And even over here, if you had one of the strong acids, then you can't just say that the whole pH will be neutral, because you still have this anion, or even cation, you still have this anion that's still reacting with the solution. So that's why over here it'll become acidic. And over here, since we have a strong acid and strong base, like we said, those turn into a neutral pH. And that's why we put neutral over here. And let's look at this one, D over here. So what we have is KOH And K, that potassium is a strong base, or it's a group 1 element, so we can write that off. So that's a strong base. But NO2, if we do HNO2, doesn't really look like it's a strong acid. So we got something right there. Now, if we write this as an ion by itself, this will be NO2 minus. And since we have a negative charge, that is an anion. Same thing over here, because we assumed it was a positive charge, so we put it a cation, and we talked about anions. You could assume that it's a basic. If you have an anion, then it's going to turn to basic solution, so this is going to be basic. All right, so now over here, we have sodium. Sodium is I forgot to change my color. Sodium is a group 1 element, and NaOH is a strong base. So that's out of the way. Now we have CN over here. Now CN is if we do HCN, that's a weak acid because it's not one of our strong acids. So CN minus, that is an anion. We talked about anions equal basic. So this is going to be basic as well. Basic. So hopefully I didn't overcomplicate this, because the only thing you need to know is that if it's a group 1 or group 2 element, then it's going to turn into a neutral pH. If it has one of these anions that pairs up with a strong acid, it's going to be neutral. But if we have a cation, that produces an acidic solution. If we have an anion, that produces a basic solution. So that's really all you have to know towards breaking these down, and it becomes really easy just through practice. So as long as you get as much practice as you can, then you'll be able to identify these much easier. So hopefully that helped you understand how to basically go about these salt solutions, because they are really different than our water solutions that we're used to. So just remember that cations, when they react with water, they will produce an acidic solution, and when anions react with water, they produce a basic solution. Hopefully you guys learned something, and as always, a Pomodoro day will make you a doctor someday. I'll see you guys in the next one.